Good evening, everybody. For those of you who are guests this evening to CCA, I'm Isla Berman, the Director of Architecture. It's with great pleasure that I'm able to welcome Guy Nordenson to CCA as our first lecturer of the series this year. This semester, our lecture series is going to be focusing on technologies and ecologies. And Guy Nordenson, a structural engineer and professor of structural engineering and architecture at Princeton, is perhaps the ideal candidate to position this trajectory. After studying at MIT and UC Berkeley, Guy began his career in the office of Buckminster Fuller and Isamu Noguchi. In 1987, he established the New York office of Ove Arup and Partners and was the director there until 1997, when he began his current office of Guy Nordenson and Associates in New York. Guy's list of projects and accomplishments is truly astonishing. He was the structural engineer for the Museum of Modern Art expansion in New York by Taniguchi, the Jubilee Church in Rome by Richard Meier, the Simmons Residence Hall at MIT by Steven Holl, and over 100 other significant projects and competitions. Recently completed works and current projects include the new Museum of Contemporary Art in New York, the National Museum of African American History and Culture in Washington, the Athens Waterfront plan in Greece with Renzo Piano, and the Asian Cultural Complex in Gwangju, South Korea, among many other projects. Guy has been the recipient of numerous awards, including being the first recipient of the American Academy of Arts and Letters Award in Architecture for contributions to architecture by a non-architect. He also received the AIA's 2009 Institute Honors for Collaborative Achievement Award, an honor given to only 7 structural engineers since its inception. He is one of very few engineers whose work crosses over into many disciplinary domains. He was the co-curator of the Tall Buildings exhibition at MoMA in 2004. He was also the editor of the book 7 Structural Engineers, the Felix Candela Lectures, published by the MoMA in 2008. Among his many achievements, Guy is also active in earthquake engineering, and in the aftermath of 9/11 led a volunteer effort to triage 400 buildings impacted by the World Trade Center collapse. More recently, his research project on the water, a model for the future on the New York-New Jersey Upper Bay, winner of the La Trobe Research Prize, served as the inspiration for the MoMA exhibition Rising Currents of 2010. Guy worked with ARO and Catherine Sievet's studio, a collaborative team of architects, engineers, and landscape architects that designed the Palisade Bay proposal that was focused on adaptive soft infrastructure. The proposal called for the renewal and expansion of wetlands, ensuring a porous boundary of piers, parks, and tidal marshes that included wind and algae farms, oyster beds, and tidal turbines along the New Jersey and New York shoreline. This project and the range of work within which he has been involved is truly extraordinary. He is also perhaps one of the few structural engineers that I know of who refers to earthwork artists such as Robert Smithson for inspiration. Please join me in welcoming Guy Nordenson this evening.
Thank you very much. It was great to come through the building with the raking light. This is a beautiful spot you have here. The talk I want to give tonight is titled Patterns and Structure, which is also the title of a book that was published earlier this year by Lars Mueller, which is a collection of essays going back a number of years, including a lot of work that came out of the time that I worked here in the late 70s, early 80s for the firm Farrell Elsesser. And it's here really working there and also with the Structural Engineer Association of California that I began to really become fascinated with structural engineering. I wasn't a very good student at Berkeley, and so it was really the experience of working in particularly the earthquake engineering field and the sense of common purpose and collaboration that is so important in that field. So it's great to come back to San Francisco and to be here again after all these years. The ideas that I've discovered over the years working in this field organize themselves around a number of concepts that actually, for me, began through my exposure to literature as an undergraduate and thereafter, and in particular the work of Ezra Pound and the concept that Pound used often of a vortex. The idea of a vortex in his case was a historical idea which represented what he saw as key moments of, in fact, collaboration in a sense, though he didn't use that word, but moments where there was a convergence of opportunity and talent that made for a significant difference in the course of art and literature. And I've often found that successful projects have that quality of serendipity in a way, where it just so happens that lots of elements come together in a magical way. Pound used as an example in architecture this notion, the Tempio Malatesta in Rimini, which was a significant work in the Renaissance history. It was designed by Alberti, but it also incorporated the work of a number of very important artists, and in itself was quite unusual because, if you can see here in the image, it was effectively a wrapper around an existing Franciscan church. So the brickwork that you see in the middle up there was a church that was there first, and Alberti's commission was really to wrap this new marble wrapper around the existing building. So one of the first cases of that kind of hybrid condition. And inside, there's a beautiful fresco by Piero della Francesca. There's a lot of work of Duccio and other artists. And what was magical about this to Pound was the fact that this situation created an opportunity for the convergence of the talent and creative energies of all these different artists coming together into this one instance. In this case, and that was actually somewhat representative of the conflict and tension in Pound's career. In the case of the Tempio, it was made possible by a rather tyrannical and brutal condottiere, Sigismondo Malatesta, who was a warrior and a brutal one. And in fact, on one occasion, when Alberti said that he needed a particular marble for the church, but it was inaccessible because it was on somebody else's property, Sigismondo said no problem and went and invaded that area so that he could get the marble for his architect. So the ideal patron, perhaps, but also a conflicted situation, as you can imagine, and I think leading to Pound's rather problematic relationship with Mussolini as well. So there's a romanticism to this idea which one should also be careful about. A more contemporary or recent example, which I think bears some of the same conditions, is the Phillips Pavilion that Le Corbusier designed for the Expo in Brussels in 1958. And there's actually a fantastic book written by Mark Tribe on this project a number of years ago. And it's fascinating because of the collaboration, somewhat difficult collaboration between Xenakis, who was then an architect before he became a composer, and Korb, who was very busy with Chandigarth and so not always around. And so when you follow the history that Mark Tribe has written about this, you can see the multiple influences that come into play. Korb had done these diagrams in the upper middle, which was his notion of this exhibition space as a kind of stomach, people coming in one end and being expelled out the other. and then inside was this extraordinary multimedia experience with Godzilla happening on the screen on the right, this platonic object floating overhead, very much of a sort of early happening multimedia experience. Xenakis, I think this is what Tribe implies, pretty much designed the form off of that plan notion, and was convinced that it was possible to make this in some kind of tension structure, and the little model on the right was his model. In the end, though, they went through quite a number of trial and error back and forth with contractors. They first worked with Eiffel, the successor firm of Gustav Eiffel. That didn't work out, so a steel structure wasn't happening. They gave up pretty quickly with the idea of tension because the shape really didn't lend itself to that. Finally, they found a Dutch firm that figured out how to make this shell by casting a series of blocks, tiles almost, on a sand dune that they built to the shape of this hyperbolic surface, and then transporting those tiles and erecting them on this wood scaffold that you see on the left there. So you have in the history the complex interaction between Xenakis and Korb, one which in the end really did not work out happily for either of them, and then the sequential experimentation that they had to go through in executing the thing in the end. Similar case is the Pavilion a few years later in Osaka that Billy Kluver, engineer at the Jet Propulsion Lab down in Pasadena, organized with Bob Rauschenberg and a number of other artists. It was a kind of origami form of prismatic shapes bathed in mist. So they had a constant fog around this. And as you can see on the left, these are images taken from the book Pavilion by Billy Kluver on this project. It too had the same metaphor of a stomach. You can see here the outlet tube where the happy tourists were ejected after their experiences. And here clearly it was very much in the spirit of the happenings that were being created through Rauschenberg and others in Los Angeles through the what was it called, was it Engineering, Art, and Technology or something like that? EAT, I think it was called, their group. Both are I think vortices in the sense that they have both this quality of convergence of talent, but also some of the complex and difficult histories. I think with the Phillips Pavilion, it was not an entirely happy history, and maybe part of that problematic is it gives the intensity to the project. A happier case is the Menil collection in Houston, but also one which I think is significant because of the moment it occurred. You probably know the story, but initially the Menils had commissioned Louis Kahn to design a museum for them after seeing the Kimball, which had been completed. He was developing the design for them and actually did a number of sketches that have been published since. Top lit. Together with the Menils, he came up with the idea that the art would be housed in a kind of treasure house and that it would be cycled through the galleries so that there was this combination storage and exhibition space, which was part of the notion. Unfortunately, midway through the design process, Mr. de Menil died, and Kahn actually described the experience as having shown up at the house with a roll of drawings under his arm and knocking at the door and being told by the butler, terribly sorry, but Mr. de Menil is dead. End of commission. That was in fact the end of the commission for Kahn, and then several months later, unfortunately, he died as well. So the project ended at that point, and only a number of years later was brought back by Mrs. de Menil, together with Pontus Hulten, who had been the original director of the Pompidou Center, Beaubourg Center in Paris. Hulten recommended piano, and piano was hired and started with the project. absorbing through the conversation with Mrs. de Menil some of the ideas that Kahn had suggested, the top-lit condition of the Kimball, but also this notion of a space that would have a rotating exhibition, and the idea of this rather intensely lit space with top lighting that you have in the museum is in part enabled by the assumption that the art wouldn't be in the spaces for very long, that it would be rotated out, so they would allow a lot more light on the work on the basis that its time in the galleries was limited. And it has also this extraordinary storage and conservation center that you can visit, so you do also have a feeling for the whole kind of biological cycle of art built into this project. Now, a key aspect of this, of course, was a collaboration with Peter Rice, the structural engineer who was a close friend of Piano's, and Tom Barker, the mechanical engineer who worked closely with Peter, who together conceived of the use of this top-lit space as a way of also capturing the heat under the glass and recycling the heat into the cavity and below the floor and using it to condition the space through a displacement system. This was the first of that kind. And also, very important and part of the ongoing work that Piano and Rice did together was the notion of using a unique material and experimenting with that material. So in this case, the ductile iron that was used for the metal elements of these leaves and the ferrous cement that was used for the bottom part. Originally, they thought the ferrous cement was going to get made in Houston. Piano had a rather romantic notion that Houston, being by the water, had some thriving boat building business that he would be able to tap into. Ultimately, they found they couldn't find anyone to do it. In fact, they couldn't find anyone in the U.S. to do it, and they found a British firm that did the ferrous cement leaves, but using a patent that came from the U.S. One of the things that Rice pointed out very often was the fact that as the leaves were finished, it's a spray-on cement onto this net of wires, that when they were finishing it, they brushed it, a different workman would brush it in different ways, and he could tell, looking at the way the light was reflected, which workman had actually worked on it. Rice was fascinated with what he called the trace of the hand, and I was having an interesting conversation before here about what happened to the C in CCAC, and I think in a lot of the work that Rice did, there is this very strong Victorian Ruskinian conviction that seeing the evidence of the craft was very important for Peter Rice, and you can see that in the Pompidou and many other projects. So resisting the abstraction in a way that was very pervasive at that time. Another. So it's a longer story around the Menil, but you have the influence of Kahn, you have the way in which that influence is brought to bear by Mrs. de Menil. You also have Philip Johnson, who had done a house for her a number of years before, and the beautiful house which you can visit now, and that design was also brought to bear, as well as through Johnson, the influence, of course, of Mies. Menil had hired Johnson originally was planning to hire Mies to do the house, but was told that by hiring Johnson she could get Mies at half the price. So hired Johnson and got him his first major commission in Texas. But you also have Pontus Hultén, you have Walter Hopps, the great museum director from Pasadena, and many other influences converging on the Menil. So again, a situation where there's a tremendous energy getting funneled into this project from all kinds of different historical influences. And of course, the fact that it happened at a very key moment in the architect and the engineer's career, where they were ready to take a turn from the kind of work that they had done before. Now, I think you can find in the work, too, the evidence of this kind of complexity and convergence. I think if you look at Crown Hall, there are some layers of meaning that are significant and ambiguous. This is a photo of Crown Hall under construction. If you look at it now, you come onto it and you feel very clearly the hierarchical organization of the structure. You have these major plate girders that are supporting the roof, that are supported on columns, and then adjacent to that, smaller elements which are clearly part of the cladding. So there's a clear distinction between primary structure and secondary structure, and your feeling is that there must be a corresponding hierarchy in every aspect of the detailing. Well, it's not quite so simple. If you look closely at the details of how the mullions are attached to the channel member that creates the fascia all around, they're all welded on there. So there's actually no separation, and those mullions are functioning as a minor part of the structure, but still a part of the main structure supporting the roof. In particular, when you look at the end, for example, here, this is the last girder. These members, which appear to be cantilevering beyond, so if you look here, the diagram would suggest that the roof is coming out to this point and then continues and reaches out as a cantilever. In fact, because of the way that the mullions are attached, the mullions are simply supporting the ends of those cantilevers, so they're not really cantilevering. So you have a lot of ambiguity in the way that the primary, so-called, and secondary structure interact. You've also got a very interesting phenomena, which is the risk of these girders, which are spanning quite a long distance and putting, through their bending, compression along the top flange. The risk of that top flange perhaps buckling. And in fact, the contractor, if you go into the archive, there's a correspondence between the contractor and Mies about the contractor's worry that these top flanges are not braced and this structure is going to fall down, and a letter that comes back from Frank Kornacher, the engineer, saying, no, in fact, this is all very well thought out. There's a moment connection here between these purlins and the girders, and so they're actually being clamped and held from below so that they don't roll over, so there's no lateral torsional buckling. But visually, at least from an engineer's point of view, there is that sense of instability that exists from the fact that these things are proud of the roof and don't quite look right in that sense. Now, I think with that in mind, when you look more closely, and here you can see the weld connection between the fascia and the mullion, that ambiguity is very productive, that it makes the building much more effective and powerful. And if you look at it from the outside, you clearly see where the primary structure is and the secondary structure. But once you go inside, that all disappears. So when you look back, you can't find the columns anymore. All of these are effectively the same scale. And if you look at the detail of the ceiling as it comes out to the end and turns up, allowing the light to come in, you really have this feeling of a kind of cloud of light all around this that's as if almost levitating the roof. So I think that ambiguity in the detail is actually consistent with the ambiguity in the visual effect as you go from the outside, which has this apparent hierarchical organization, to the inside where it all disappears into abstraction. So here again, this is primary column probably, but still I think the scale difference between is such that you really can't tell, and it all looks like it's being held basically held up by the facade. A similar situation with the Beinecke that Bunshaft designed for Yale. It's a very simple, clear diagram. You've got a Virendale box, a rigidly connected grid of steel that's wrapping around the entire, what he called treasure box, which was containing the rare books. And it's supported very cleanly on the four corners by these little pyramid and bearing details. Well, if you look at it more, and there's this beautiful sort of collapse of the structure and the light shading and the skin in this, where you really can't tell them apart. If you look at, the shadow pattern is reflecting actually the tapering of the structure that corresponds to the moment diagram, but also as you'll see the way the light comes through into the space. I don't think you can read distinctly the structure in this case as separate from the skin. Now when you get and you look at photographs of it under construction, you can see there's the grid around, and then the corner member is quite skinny, and that's because it's being held actually below, as you saw in this image, it's being held back from where the structure is. So, in fact, you've got this wrapper all the way around that's holding up the majority of the weight of the building, but the support isn't even under that wrapper. It's held back, and it's held back for compositional reasons to keep the overall relationship between the support and the box more feeling more appropriate. If you've been to Cornell, there's another building that Bunchap did where the supports are actually out at the face, and it looks quite a bit clumsier. So I think by pulling them back, he got the right effect for the building, but in so doing, he completely contradicts the logic of the structure, and you see that in that very skinny corner element and that little cross piece there. So again, there's this tension between the way in which it's functioning, which is a strong part of its expression, and the way in which some of the moves are made. Again, coming inside, you see the light coming through the marble, and then also, I think, you can sort of see it in here. You have the same effect of light, very bright light coming in below that you get at Crown Hall, giving the sense that the building is almost on a pillow of light. Finally, in this sort of series of precedents, the World Trade Center towers of Yamasaki and the structural engineer Leslie Robertson is, I think, in a way, the best example of where tectonic and craft and abstraction come together in a very interesting way. As you probably know, the structure was all around the facade, a grid structure, tube frame, perimeter tube frame. So it made the building effectively work like a perforated tube with all four surfaces functioning as part of the strength and stiffness. Robertson developed an extremely sophisticated and original system for this. Every element was thought through and customized. The facade was made out of plate steel welded into these trees, as they call them. The beams are actually just vertical plates without flanges because they're spanning so little that they don't really need that, and they're merged into the back plate of the box columns. These are access holes to make the connections with the stack above. Everything was very, very carefully crafted. And then also the panels for the floor were prefabricated with the truss and the slab integrated together, and so on. So it's a masterwork of invention and originality. After 9/11, when MoMA organized a show on tall buildings that I helped with, I wanted to do something that would represent what I thought was the originality of this project. And with students from Princeton, we made these drawings which mapped the different types of steel that Robertson had used to make the structure. As it turned out, he used 14 different types of steel, much of which came from Japan actually, going from standard 36 KSI steel all the way up to 100 KSI steel, and deployed it in the perimeter structure in a very interesting and original way. There's a classic problem with tube frames that when you look at the analysis, even though it's meant to work as a kind of box structure, you find that a lot of the stresses end up being concentrated in the corners and don't find their way very well into the middle of the front and back face, the leeward and windward sides of the tube. It's something called shear lag. What Robertson did to overcome this was to use the high-strength steel in the corners, and so by that was able to match the stress levels that were in the corners, but do it with smaller plate elements. Because they were smaller, they were more flexible, and because they were more flexible, they would shed load. And so by making them stronger and smaller, he was able to rechannel loads away from the spots where it wanted to go back into the middle of the faces of the building. Now, he was responding to the stresses that he was getting from it as analysis, which correspond to the wind tunnel studies that had been done, in fact, for the first time on this building. This was one of the first buildings to initiate the use of wind tunnel studies for for tall buildings. Now, if you remember, there were two buildings, and the two buildings were oriented in a particular way in the wind environment in New York. And so they sheltered one another, plus they had stronger winds coming off the water and stronger winds coming from the directions of prevailing winds. So the wind loads on the structure were coming in a very complex way, and so the analysis would reflect that, and the stress patterns would, in other words, would also reflect that as well. So he was both expressing and manipulating these effects. This shows you these are the different types of panels of which the facade was made, or the perimeter structure was made. These are the different steels coded by color from the low strength to the very high strength in red. And these are some close-ups of the drawing that we did. So you can see the deployment, and the deployment of the different types of steel, again, is a design decision to move stresses around the structure, but it's also a reflection of that complex environment that was studied through the wind tunnel. It's a very beautiful, to my mind at least, it's a very beautiful work of design and attention, and yet it's completely invisible. Now, there's a quote that Wittgenstein used a lot, which came from Longfellow, which goes like this: "In the elder days of art, builders wrought with greatest care each minute and unseen part, for the gods see everywhere." And I think part of the point here is a historical point about convergence of force and opportunity and talent. But part of it is also represented in what Robertson did for the tower, which is the intensity of invention that can be applied to something that is completely invisible. And that, I think, is a significant point to remember. So I'd like to go now through quickly through a number of projects that we've worked on, some of which from my office, some of which when I was working at Arup in New York. Starting with the MoMA, to show ways in which I think these can be read perhaps in a similar way. At MoMA, we worked on the preliminary design with Taniguchi. The final design was done by KPF and the engineers Severed Associates, and we, for the most part, were helping organize a kind of the geometry of the structure in a way that was as simple and clear as we could make it. So much of that is not really apparent or visible in the final work intentionally. I mean, given the architecture of Taniguchi, it was definitely meant to be sublimated. But there are a few points where we did contribute that are still visible. One is in the design of the walls facing the garden. Taniguchi had done a very beautiful museum in Tokyo for the Horyuji treasures, where he used steel plates as vertical mullions spanning a very long distance, and it had been completely welded up in that case. We wanted to do something similar here, but Taniguchi was concerned that the craftsmanship in the barbarous region of New York was not going to be up to the Japanese standards, and so we had an uphill battle in convincing him that we could try the same thing. And in the end, we're successful by arriving at a scheme which did not include welding. What we ended up doing, the verticals here are 2x7 solid steel bars, and the horizontal are 3x5, and the connections are mortise and tenon. So there's a machined connection. They fit together, and then they're clamped with a pin from the outside. So effectively, they work as a rigid connection, but not through welding. And these things are spanning 60 feet from the top there. This one's free span here. The other ones are propped with these little rods back, but they're still pretty skinny given the height, and so they depend on their interconnection to avoid buckling laterally under the weight of the glass and wind loads. But still very, very simple, very minimal, and in the end, I think successful, and in fact, in the end, fabricated in Germany. The other move was in the Contemporary Art Gallery, and this is a sort of moment of dematerialization. We had in the original design, we had these columns in the Contemporary Art Gallery, and there was a there was a moment where we had a meeting with the director of the museum and a number of other people, and Glenn Lowry mentioned that one of the trustees had been complaining that there were too many columns. And I didn't quite know where it came from, but anyway, I took the message, there are too many columns. So I realized at that night that in the way in which we had designed the structure, there's a gallery building down here, the new galleries, and then above that there's a tower. I think you can see here, there's a tower that goes up above, which has offices and conservation labs and mechanical spaces in the lower portion. Conservation is here, and the mechanical space is here. Because the core is quite skinny, facing the east-west direction, we included these belt trusses around the mechanical core and at the top, this sort of top hat truss, to stiffen that core. And so we had that in the design and in the budget. So I realized that we could get rid of this column and hang the 4th, 5th, and 6th floor from that truss by simply adding material to the truss. And since we'd already had the fabrication of the truss and the erection of the truss built into the budget, we were simply adding material, which is a much lower unit cost than the total cost of steel. So we went back to the director and said, well, we can get rid of the columns. And it was at a stage in the design where this seemed miraculous, which it wasn't really, but it was such that and very cheap. So like $10,000 to get rid of 2 columns. So that's not much. Now clearly the SANAA show wouldn't have looked so good if the column had remained. So this was a good thing. But the other thing that was fun about it was that it became a kind of urban legend. And so when they would give tours to VIPs during the construction, the man who would give the tours, who actually lives in the Bay Area now, he would bring them to this spot, very excited, and say, and here is where the column was removed. Of course, the VIP didn't know what the heck he was talking about, but it was a sort of sacred spot of the missing column, that had. So I was very happy about that. This is an earlier project, the dorm at MIT that we did with Steve Holl, which Steven was interested in trying to find a way to make the building as porous as possible, because it sits on the boundary of MIT to the city, and so big cutouts and openings in the design. He was also very interested in the idea of a sponge. So we were, and this often happens, and it's a lot of fun with Steven, is that there is this kind of metaphoric basis to the design, which opens a door to lots of interpretations from different from different perspectives. So we took that on, and the basic gridding of the facade that went along with that, and developed a structure which was on the facade made of precast concrete panels. And so this is it under construction. So what you see on the facade is the grid of concrete, prefabricated concrete panels that make up that structure, which facilitates the spanning over these openings here, the double cantilevers in the corners, and so on. And what you've also got here are these little spots where we also filled in, within the grid, filled in certain spots in order to strengthen it where we had high levels of stress. So we started out with the uniform grid, and then we modified that grid to deal with the stresses. This is a view from the inside. And so the panelization was 20-foot segments, 10 feet tall. The floor-to-floor height is 10 feet. So you get 3 windows per floor. So a student's room has a 3x3 grid here, 10 by 10 size. So you can pick whichever windows you want to open depending on your mood, and that's all made up of this concrete grid on the outside. Now, typically, it was hard to convince the contractor to do it this way. I mean, it was not conventional, and as often happens, so we worked with a contractor a fabricator in Canada, Bolduc in Quebec, who did a fantastic job. And in the end, it was so quick to erect this thing This is always what happens, that initially lots of resistance. This is a ridiculous idea. Why would you want to do it this way? And then we sort of were able to convince everybody that it was economical. We did it. It took them then like 20, 35 minutes to erect each one of these panels. It moved so quickly, and they needed so few workmen that they'd have to sort of wait around while the cast-in-place concrete that's on the inside of this building would catch up. So, of course, at the end, the contractor complained to me that we hadn't made everything precast. And this is there you see the seam between the panels, which was cast in place, but this is under some photographs under construction. And then the engineer was working on site. She had this drawing that she used to check to see that the rebar was correct in the precast elements before they cast the joints between them. And so she'd color-coded the different rebar. And Steven wanted to find some way to introduce color into the facade. And so in the end, this formed the basis of that color. And so the color that you see in the facade corresponds to the diagram, which corresponds to the rebar, which corresponds to the stress levels. And so as you walk around there, you're seeing mapped directly on the facade what size rebar is inside. Now, clearly, there's an MIT student there somewhere, I'm waiting for him to call, that will catch the one case where we made it the wrong color. But here you can see how this, here you see the panels that are blocked in. So these are directly related to the fact that there are high stresses in this area because of that overhang. But it worked really well to wrap the building in this grid, because it really was a good basis to start from in handling all these different conditions. Plus, it was a very good backup for the facade. So from a construction point of view, it made a lot of sense, because we put up the concrete, it became the interior surface, worked very well as thermal mass, didn't have to finish the interior, and then wrapped it with insulation and then the aluminum on the outside. So you immediately had the backup, everything ready. So ultimately it proved to be very practical. This is the final thing. A couple of years later, also with Steven, we did the Nelson Atkins Museum. This was a competition which Steven won by breaking the rules. It was meant to put the building behind the existing museum, and he came up with a really wonderful idea of having it cascade down the side of the site facing out onto the park that had been designed by Dan Kiley and Jack Robertson. So very much embraced both the building, the existing building, and the sculpture garden that's in front of it. Here you see, really these wonderful, as he called them, lenses, luminous objects that are sitting in the landscape, and then the rest of the galleries are actually underneath in this berm with open off to the side to the garden. Now, the two interesting aspects of this, one that I'll come back to, is the construction of these lenses. The other is the parking garage, which was placed behind and connecting the two buildings, actually, which is underneath this Walter de Maria piece, which is a big thin layer of water over a number of circular skylights down into the garage, and then in the middle representation of the sun. So it's like a solar system with lots of planets around it. Inside, the garage is made of also precast concrete, what we called wave tees, which were long beams that were in this shape, 12 feet wide, 60 feet long, pre-stressed, cast on these custom forms that we got from Oregon. The precaster was in St. Louis, and these are them going into place. And the nice thing about this was that we came up with the idea of supporting each one of these on its own column, so that when you went into the space, you really have this clear run of the corrugation of this roof above you. And one of the things that's extraordinary when you go here is, and which was not entirely intentional, is that because of the drainage slope of the level above, which is the plaza and the Walter de Maria piece, you get quite a lot of variation in the height of the space. So there's an amazing kind of Pyrenean feeling of compression and opening up of the space between the floor slab here and this corrugated structure above. Works very well. a lot of people. I once got this very excited phone message on my answering from Tom Main, who had just been in here and thought it was the most amazing parking garage in the history of the world. It was, so it worked, right? The other part was the design of these lenses, which are channel glass, frosted glass, 2 layers with a cavity in between. So actually an accessible cavity in between with catwalks and so on to maintain and clean the glass. And we wanted to keep the structure out of that glass zone. And so in all these lenses, the structure is concentrated down the middle. In the smaller lenses down further, we have these T's, kind of like masts, and cantilevers that hold everything up and that are just tied at the tips down into within the glass with small rods. Steven explained to me the jury was a very prestigious jury. I think it was basically the Pritzker Prize jury at the time, and one of the members of the jury was the former director of the National Gallery, Carter Brown, who was from Rhode Island, Brown as in Brown, and he, of course, was an avid sailor. And I had explained to Steven that the idea of this structure was like a mast, and that, sort of standing there like this, and that you had this trunk and then these arms like this. And so Steven recreated that explanation in front of the jury for how the structure, the T structure of these lenses worked, and that immediately won over Carter Brown's vote, because it was just like a sailboat. Oh, yeah, I really like that. So that worked. But then in this structure, instead of the central piece, we have a truss, a spine truss going down the middle. But there's the same idea, trying to gather all the support in the center, so that it then is able to have very slender members on the outside that just deal with unbalanced loads. So this is that space, and you can see the shadow is relatively light of these. They're basically 5-inch tubes in the structure, and it gathering all the load into the middle, and actually in some cases exposing that spine truss as well. Beautiful space. If you have an occasion to go to Kansas City, it's very much worth a visit. This is the church that Isla mentioned earlier in Rome, with the competition that Richard Meier won. Wonderful design of these shells nested into each other facing south. The light bounces between them into the space. After winning, we didn't really have a specific idea of how these things were going to get built when we did the competition. So we started a conversation afterwards together with the collaborators in Rome, and suggested that one way we might do this was by making them out of large blocks of prefabricated concrete that could be stacked up in a sort of very kind of Roman condition, I thought. And this caught on with the local engineers, who many of whom were disciples of Pierluigi Nervi, and so very attached to the idea of prefabrication and precasting and assembly that way. And also with the contractor Icalcimenti, which is the largest cement company in Italy, who were very excited about the idea of exposing the concrete. Initially, Meier wasn't very enthusiastic because he was worried about the quality of the finish, and so there was this back and forth for quite a while about how well the concrete could be made. By precasting it, I thought we could probably achieve a good quality. So given that principle, this is it under construction, and you can see a little bit the context here. Housing district, basically in the outskirts of Rome, a town called Tor Tre Teste. Given this approach, the contractor came up with this, Icalcimenti came up with this wonderful gantry, what we call the macchina, which was used to build this thing. And it's this gigantic gantry on wheels that would embrace each of the shells and build them step by step, and I'll show you this in a second. So this is it around one of the shells, I think the shallowest one, the first one. This is just before that, actually, and they're beginning to erect that, and you can see the tracks that it moved on. So there were 3 sets of tracks, each of which brought it over the individual shells, and it basically did the smallest one first, and then they moved it to the next set of tracks, did the next one, and then the next one. And it was designed so that it would fit in between as well. So there was a platform, and then the units would be placed inside the platform and then lifted up to their correct position. This is a sequence here, so lifting it up, getting it onto the platform, and then putting into this jig, which was on a movable platform that was with actuators moving horizontally back and forth, and then it was also able to tilt and turn. So it was a full multi-directional control, numerically controlled off a computer next to it, and able to position it following pre-programmed requirements for each shell. So the position had been programmed, so the jig was basically moving it into position, and they really only needed 3 workmen to do this. This guy with the sweater here, no hat, and then the other guys, and it took them. They would put 2 up every day. So the morning, they'd get 1 in place, and then it was time for lunch, and then coffee, and then the afternoon, the second one, and then time to go home. And it was great because it took forever. It took like 2.5, almost 3 years to build, which meant I could go to Rome every couple of months during that period of time. But it also meant that for the community around it, and particularly the children, I think, seeing this machine moving back and forth and slowly in a kind of Gothic way erecting this thing was part of the meaning of this church, and it is beloved by everybody, and I'm sure it's because of the structural system. Here you can see so the division of the panels. The post-tensioning holds it all together, so it's clamped together with cables vertically and horizontally. And actually, going back to this, you can see these are the ducts for the horizontal cable. These studs and plates make up the joint area when grout comes in to seal that joint, and then also vertically, here you can see him adjusting the post-tensioning rod. There's got a coupler in there, and as it went up, these rods would get sequentially post-tensioned, so it was clamping it down as it went up so that it could deal with the stresses of it leaning over. You know, notice there was no scaffolding or anything, so it's the sequential post-tensioning that allowed it to hold together as it went up, and then we had final post-tensioning going in secondary ducts, both horizontally and vertically to pull it together. Structurally, it's quite interesting because around the openings, it's definitely got a lot of stresses from bending as it spans across. But when you move away from the openings, you really do get shell-like in-plane stresses. So it is as if you had sort of plucked pieces of the Pantheon and moved them over. That you've really got these pieces of domes that make it up. Now the funny thing about it was that because of Meier's concern about the quality of the concrete finish, there was endless mock-ups and tests that went on and on and on. And one of the things that he was concerned about was that the concrete be very white. And they weren't able to get it, and they weren't able to get it, and somebody figured out the solution was to mix titanium dioxide into the cement mix, which did make it extremely white. Well, they built it that way, and then somehow someone discovered that this had the property of precipitating dirt in the air and suspending it on the surface of the concrete and then having it wash away. So basically it was cleaning the air, cleaning the smog. And by virtue of this insistence on the quality and whiteness of the concrete, they had invented this new kind of concrete that was going to eat smog and save the planet. And they advertise it. If you go to Talcemente, this cement is a major product of theirs and has the claim that it does great things to avert climate change, all because of this strange sequence of events. This is the final, there you go. TX Active, registered trademark, is a photocatalytic principle for cement product which can reduce organic and inorganic pollutants that are present in the air. This is how it works. So there you have the diagram. It's amazing. So this is the final thing that it's if you're in Rome, don't miss it. It's a bit of a trek to get out there, but it's definitely worth a visit, and very popular. Everybody wants to get married there. The Patent Office Building was a competition that we entered with Harry Cobb, which we didn't win. Foster won this competition and actually executed a beautiful roof that's there now. We had this notion that the character of this space in the Patent Office Building in Washington was really historically made by the presence of these two great trees. And so we wanted to come up with a design that recreated the effect of the trees and used them actually to hold up the roof. The roof also needed to be independent of the existing buildings that really didn't have, the old masonry really didn't have the capacity to support the new weight. Structurally, we developed a strategy which was based on taking the moment diagram on a two-way grid, which you see here, and then using that to form a distorted grid that would follow that pattern in such a way that if you put post-tensioning through those lines, so if you imagine those red lines being hollow tubes, that if you had a grid, flat grid, and then around that flat grid you had this structure weaving in and out, when you post-tensioned those lines, you would effectively balance the dead weight and be left with nothing but compression in that grid. So it was a representation of the stress diagram, but also a kind of activated bubbling surface created by that concept. This is the Toledo Museum, which we did with Sejima Nishizawa a couple years ago, working with the engineer Mitsuru Sasaki, great Japanese engineer who has worked for years with Toyo Ito and Sejima. We collaborated on this. This is the plan. These lines represent the glass lines, and you can see there are cavities created between each of these is a room, and then the cavity in between is used to move air and create acoustic separation. The vertical structure is all contained within those cavities and made up of 3-inch diameter solid steel bars. The roof is very thin, and so the challenge was to squeeze the structure as much as possible. We ended up with a 12-inch thick structure spanning in some places up to 60 feet, and we got that by using a two-directional grid of all rigidly connected girders and beams. So the girders, which you see going in and out here, are rigidly connected along their length, and then the beams in the other direction, spaced 8 feet apart, are also rigidly connected to those girders and to each other. So you have a kind of blanket of rigid steel up there dealing with these spans. Of course, the integration was complex, getting all the piping and everything through. Everything had to go into the same space, so a lot of time was spent. This was not a BIM project. We just figured it out by hand and elevated all the beams. So on our drawings, we showed every single hole, and it worked out. But there you see some of the conditions. And here you can see in the corner there, that's a connection of one of those columns. It's a pin connection so that the column is free from the roof, so when the roof moves, it doesn't put some bending into the column. A lot of coordination had to go in just keeping in mind the thickness of the gusset plates and the bolts and everything, because glass in some cases had to go right by underneath within quarters of inches of where those bolts were. But the effect in the end is quite good. I think that you can see that the structure really disappears. So that the thinness, but also the way in which it is slightly disordered in its arrangement, you completely lose track, and you feel like this basically is held up by the glass. We've done a number of projects recently with Michael Maltson. This was in Fresno. A museum project that is pending still. basically this volume up in the air on a limited number of feet, which we developed into a series of intersecting trusses, creating the rooms of that space. And then more recently, the administration building for JPL, where the structure is essentially a crisscross of two lines in each direction with what Michael was calling a confetti of trusses, of diagonals scattered in between. And for an exhibition that Michael had in Montreal, we built a model in the office which represented the stresses in the structure through a somewhat complicated but I think attractive coding system to show how that was working. This is a pair of bridges at Yale that were completed recently. The commission came through Cesar Pelli, who was advising the university and proposed that in replacing an existing pedestrian bridge, instead of which had sidewalks, instead of having the new one with sidewalks that would separate the pedestrian from the traffic. It's a fairly short span, about 60 feet over a canal that's actually been decommissioned, and it's now a bikeway. And so we had two bridges to do on either side of this new bridge, and it's in a setting at Hill House Avenue, which is quite beautiful and old, a lot of old houses there. So there was a desire that this have a certain traditional feeling to it. And so we took inspiration from bridges that had been built in the Victorian era. This is at Regent Park in London, which are sort of the typical lattice grids making up a girder. But here you can see, first of all, it has these stiffeners as well as the lattice, and then these outriggers that are used to stabilize the structure. In our case, what we tried to do was eliminate those by corrugating the web and using the corrugation as a way of providing that lateral stability. This is the structure. Basically, that grid works as a Virendale. But here in plan, you can see there is a tight corrugation in the middle where it's stabilizing the top truss, so that crown hall problem of lateral torsional buckling, holding that top with the corrugation acting as a vertical sort of folded plate cantilever. And then at the ends, the corrugation works to keep the web itself from buckling under the high shears. So you get that variation from the tight, looser, and then tight again in the middle. This is a mock-up. The fabricator was amazing. He built a full-scale mock-up just to see whether he could do it. So it's available if you want one for your backyard. And everything was numerically controlled. I mean, obviously the cutting, but also the brake press used to bend these things, very tight tolerance, and especially a lot of attention to controlling the heat input in the welding, because very thin plate, it's 1/4 of an inch thick, so easily distorted if you don't. This is it being installed, and it has a wood sustainably harvested hardwood deck. But you can see a little bit here. It's a little hard to photograph, but the effect of the corrugation, first of all, the way the light comes through is quite dramatic, but especially gives you much stronger feeling of the thinness of almost paper thin quality of that web. I think this is the last project before I go into a little bit about the climate change stuff that we did. This was a theoretical project a number of years ago, which we were doing for the Port Authority, looking at the possibility of siting a new TV broadcast tower here on the tip of the Bayonne Pier. And we worked on a design that we'd initially done with Harry Cobb for an issue of the New York Times Magazine that Herbert Mouchamp did in 2002. And it was going to be sited right next to the stock exchange, but again, it was going to be a broadcast tower. And we developed this idea of a structure made of stems or straws almost, that would twirl past each other, creating a void space that was, in fact, the design. So very much organized around the design of the negative space between the elements, and a space that would have a variable aspect as you moved around the city. So looking to achieve something that was quite different as you moved around and saw it from a distance. There you can see also the way in which tied together with a series of horizontal beams every 70 feet, which the tubes are 21 foot diameter. These are 70 feet apart. And these were also intentionally left open, so they would capture all the stems as it went up, as they moved around, but never entirely closed. So a lot of effort in maintaining this sort of sense of openness. Now, from an engineering point of view, one of the things that we started to explore in the application at the Bayonne site was the possibility of trying to design the arrangement of these stems in such a way that we would gain some benefit from their position relative to the wind. And we took inspiration from some studies that had been done for suspension bridges, looking at the effect of the wind on paired suspension cables, which had discovered that, as you would expect, when they're far apart, they're basically independent. When they're very close together, it's as if you had one. And it turns out if they're slightly apart, 3 diameters apart, the drag is actually less on 2 than it would be if you only had 1. So somewhat miraculous aerodynamic effect. So there's a benefit to more, to collaboration, right? There's a benefit to 2 over 1. So taking that idea, we wanted to develop a positioning of these stems in such a way that the drag would be least in the direction of strongest prevailing winds, which for New York, for hurricanes, is from the northeast. This is the windrows for New York. So we did some work with wind tunnel, RWDI, doing some CF computational fluid dynamics studies to try to see what some various kinds of patterns would provide in terms of drag. And then together with the engineer Ted Zoli, Ted came up with a very sophisticated calculation method using actually that original research to figure out ways to predict what kind of, we called it drag rows, would result from a particular arrangement of stems. And these are the surfaces of his computation. But effectively finding a way so that the least drag would face the greatest wind direction. And in a sense, you would then have a representation, in a way going back to what Robertson had achieved with the World Trade Center tower, a kind of representation of the environment within the characteristics of the structure. Now the last part I'd like to show you is the work that was mentioned regarding climate change. This is a project that we, my wife, Catherine Sievert, and I started a couple of years ago. We received a command. This is our dean called us and said, "You will apply to the La Trobe Prize. You will figure out a topic." This is how it works, right? So we were sitting at the table, looking at each other, figuring out what are we going to do, and could we figure out something? Could we come up with something so that we actually don't get it? Because we really don't want to do this. Got enough on our plate already. So we applied with the idea of actually inspired from that tower project and the positioning of that tower project. It got me thinking about how this body of water in the New York area was really under realized. I mean, people didn't understand and didn't think about it as a place in the region. So somehow or other, we came up with the idea of that, the notion of trying to redefine that place, and the problem of sea level rise, and figured out a way to sort of combine the two together and applied. And in fact, we didn't hear anything back, so we were hopeful that we might not get it. And then the letter turned out to have been lost, and then it was too late we got to the second round, it was too late to apply to the second round, so I called him and said, "Really sorry, we can't apply to the second round." He said, No, we'll extend the deadline. So then we teamed up with Adam Urinsky and went down and interviewed. And what was remarkable about it, I mean, in the end, it caught on, and we were very excited about it. But what was remarkable about it was that the fact of taking climate change as a fact and trying to figure out how to develop an adaptation strategy at the time, this is about 4 years ago, at the time it really wasn't, it was unexpected. And I could see when we were talking to the jury that people were quite moved at the notion that this was something that could have a certain optimistic dimension to it, that this would be something that one could, in a sense, work with to find ways of not only addressing the problem, but also creating benefit on a number of other fronts. So the initial premise was to take this place, which we defined as sort of Dr. Seuss looking figure, which we became quite obsessed with. Beautiful, isn't it? And identifying this as the place that we wanted to work with. The problem of sea level rise, which is on the order of 2 to 3 feet in the next 100 years. The current problem of flooding, and you heard about that recently with Hurricane Irene. Clearly the mayor decided to react as forcefully as he did to that hurricane because of the MoMA show. But these are the flooding patterns that are predicted now without taking into account sea level rise. So already we're quite vulnerable even to Category 1 hurricanes, which is the red portion here, and especially for the higher hurricanes. Now, one strategy to deal with this is to block it off, and there's a very good group of coastal engineers at Stony Brook, SUNY University, State University of New York, Stony Brook, who have developed a strategy based on putting barriers in these locations which would keep the water out of the inner harbor, using basically the sort of Dutch approach of big gates that would be deployed in the event of a major storm. Our strategy wasn't so much to deny the possibility of those kinds of hard infrastructure approaches, but to say that at least there ought to be, alongside that, or maybe replacing that, what we call a soft infrastructure approach, which was effectively the use of all kinds of different strategies to dissipate the energy of storm surge. So basically barrier reefs, barrier islands, ways in which we could reduce the impact of the storm, but not necessarily try to block it entirely. And so this included islands and various treatments around the edges. So big islands in the middle, in the shallow areas of the bay, and very small islands along the edges, all with the intention of sort of roughening up the edges and creating obstacles in the middle of the bay. We were also, and this is sort of the duality of the strategy, we were also trying to define a new center, a new void in a way, that would have an analogous impact to the effect of Central Park in the 19th century. If you look at images of Central Park as it was being developed, it was a void inside an emptiness. I mean, there was none of the definition that you have now with the city that has grown around it, and it created, though, that clear space around which the density and concentration of the city would organize and became, as it is now, this amazing public space for Manhattan. The water can be a place like that, and Venice shows that the water can be occupied, can be a public space and a public place as much as land can, and so our inspiration was very much the basin of St. Marco as well. So in the research work that we did with students over, and a number of them are here actually, over a couple of summers, we mapped the edge, looking carefully at what the existing conditions were, looking at the fact that the edge had varied over time. This is a superposition of the edge over the course of about 80 years, and it's extremely dynamic, and yet there's quite a conservative attachment to the way it is now. You know, the environmental groups and other groups really trying to fend off bad things, which have happened all too often, have also become extremely attached to the condition as it is today. And this was trying to loosen that up a bit and show that a certain dynamic aspect of that was manageable. We developed an atlas of the bay using various aerial photography and others to identify the edge conditions and start to map actually the height of seawalls and other conditions, and also overlay on that the flooding that would happen, the 500-year flood and the 100-year floodplain. And keep in mind that with sea level rise, essentially what happens is that what is now the 100-year flood plain becomes more like a 10 to 30-year floodplain, and the 500-year floodplain becomes effectively the 100-year floodplain. So the issue here is not only the storm, but also the increased flooding. And we have an extremely inconsistent design of the boundaries. I mean, there are places where there are seawalls, but then right next to that there's nothing, and so the water can obviously find its way around. There's no coordination. This takes you across, as you can see on the upper left, takes you across our atlas. So the purpose of the atlas was to begin to define what was there, both as a setting for new strategies, but also to facilitate the creation of a digital model. This is the bathymetry, the underwater terrain, and then combined with the topography was used to do some numerical simulation, but also to get us thinking about the continuity of the space of land and underwater, not, again, undermining this, trying to break down this notion that the waterfront is somehow a hard edge. A number of tools that we'd used on earthquake engineering projects, actually some planning projects we'd done a number of years ago. We had a database of all the buildings in New York, at least, and started to try to develop one in New Jersey, which we could use to look at the consequences of various scenarios in terms of damage or reduced damage to the existing built structures. This is from the fluid dynamic models that were made to try to study the effect of putting islands in the way of the flow. This is the model on the left that was developed by colleagues in the civil engineering department at Princeton, working with, again, a sort of abstract representation of our island idea. We actually got our very own custom hurricane generated by the Geophysical Fluid Dynamic Lab at Princeton. Brilliant student who's now at MIT. She took Hurricane Isabel, displaced it over, and then modeled the track of the hurricane coming in to New York as a way of generating the storm surge, so getting the input of the storm surge coming into our model for the bay. So trying as best we could to come up with a solid foundation for some of our arguments. And here you can see this is what it says here, all island, and above that New York Isabel. So the magenta is with islands and the blue is without islands. You can see the storm surge is the same. The amount of water, you're not going to stop the water unless you stop the water. So we're not saying that we stop the water. We let the water come in, but the effect of the islands is to reduce the velocity. This is charting the mapping the velocity. So by reducing the velocity, surface wave velocity of the water, we're reducing the energy and we're reducing the damageability that results from that. That is our theory. Now it turns out that we happened on an area of science which is totally underdeveloped, and so we've sort of identified an area that needs a lot of work in computational hydrodynamics in getting a better handle on what happens when you let it go. You know, we do a really good job with river modeling and oceanfront modeling when we have a hard barrier, and we can treat like the San Francisco Bay as a bathtub. We know what happens when the water flows in and out, as long as that edge is hard, because we're used to hard edges. That's the way we like to engineer it. The minute you make that edge soft, or you allow the water to overflow in a tsunami or something else, the modeling of what happens when the water goes over the boundary layer of the ground and buildings and other obstruction is just not there. And in a sense, it's like the wind tunnel work before there were wind tunnels. You know, that the invention of boundary layer wind tunnels was to try to do tests to see what happens when the wind goes over cities. And we're kind of at that very early stage in this area as well. So these are some maps of the design, including some suggestions for transportation inspired by Venice. I think the mental map of a place has a lot to do with the transportation system. And if you think about Venice, the different vaporettos in Venice have different circuits, and you really start, when you get used to it, you start to think in terms of the city as accessible along these different lines, that either bounce back and forth along the Grand Canal or go all the way around. A little bit like the subways in New York, map for you the city in a sense. Some images of parts of our proposal. The statue looks great next to these wind turbines. We currently export subway cars for reef making off of New Jersey. We should keep them, use them ourselves. These are islands of wetlands. Wetlands are going to be submerged by the rising sea level, and so the barrier islands can, in fact, become replacement wetlands. And then this is a beautiful design that ARO did for Lower Manhattan, showing how this system of barriers could look, making them. We're actually starting a project pretty soon with the Port Authority, who's gotten very excited about this, wants to reuse dredge materials in this fashion to test making islands. This is some of the studies that ARO did, looking at a little water table to generate some formal ideas, which they then turned into this design. And then finally, just briefly show you an exhibition that we did last summer, not this summer, but the summer before, in Venice. We were asked to, Jonathan Solomon was organizing this and asked us if we would present our New York project, and it was kind of simultaneous with the MoMA show, Rising Currents, so it seemed a little strange to just show that by itself in Venice. And so we teamed up with friends at Louisiana State University and came up with an exhibition based on the juxtaposition of our project and ideas that they had for the reconfiguration of the Mississippi. Actually, no small plans. Catherine Sievert came up with the idea that we would make these side-by-side models that would express the continuity of topography and bathymetry that I showed you in the digital model, and then objectify the water as a separate element floating above. And so these two models on the left is the Palisade Bay, our New York project. On the right, the project for the Mississippi. So this is again that computer model, which then was translated into this model that you see on the left with the water floating above. This was made in lightning speed by students at Princeton. The thing about the Venice Biennale is that they announce who's going to be in it like 3 weeks before you have to ship it, because of course it takes forever to get installed in Venice. So we had very little time to do this. We built it in these 5-foot square segments. So each of these units was separable and shipped. And we did this on a scale where we exaggerated the vertical scale relative to the horizontal scale. So actually the vertical scale of both models is the same, but the horizontal scale by necessity, of course, is different, both from the vertical scale but also from each other. So the horizontal scale, of course, for Mississippi is very different from the one for the New York Harbor. But in both cases, the vertical scale is exaggerated and the same, which is why you get this really strong depth feeling. This is the Bayonne Piers. That's Governor's Island. This is the shallows in front of Brooklyn. That's Lower Manhattan. So these cliffs are an exaggeration of the vertical scale, but quite beautiful. And then on top of that, the plexi model representing the water body at the same scale. So it fits into the piece below, and then in green showing sea level rise and flooding expanse of water as well. It was fun, we watched people. They would all crouch down and try to figure out what it was. It was somewhat mysterious, which I think caught people's interest. Now, the project for the Mississippi was the idea of a coastal engineer named Bob Twilley, who was at LSU, and his notion is to figure out a way to redirect the water and the sediment from the Mississippi that's coming down at the moment through the channel and getting dumped off the continental shelf. You can see it there on the lower right, and find a way to deploy that sediment and water in such a way that it would do a better job of rebuilding the wetlands that are getting lost in the delta. And so we identified 5 different places where these diversions could exist, and these are rendered in the colors of the Olympic, the 5 squares of the Mississippi Olympics. As you know, the Mississippi has moved around over the years, but at least until this last century, when it was put under much more control by the Army Corps of Engineers. And so now it flows down this red line and out through what they call the bird's foot, and dumps all the sediment uselessly out past the continental shelf. Clearly, this is, the key here is navigation, and so the tension is between maintaining navigation and finding ways to use the sediment more productively. These are just some maps of, this is the petrochemical infrastructure, and which is totally at risk. So it's not in the interest even of the people that use this for industry to let it continue as it is, because it's putting all the infrastructure out there at risk as well. So moving from left to right, Wax Lake is actually an existing diversion that is there now, which is working at diverting water from the Atchafalaya and building land quite effectively over the last 10 years. So an example of how this can work. This is a representation of how much land could be built over the next 30 years. This is moving over to Terrebonne Basin. This is the intercoastal waterway up here. So using the waterway as a way of diverting more water then down through a new channel that would come out here and drop sediment there. This is going through the Bayou La Fouche, which is an old, like all the bayous, is an old path of the Mississippi. So trying to find a way to reestablish this as a channel. Of course, all this has huge implications in terms of infrastructure development and also impact on existing settlement patterns. But it's a strategy, a visual strategy that's trying to put down a hypothesis that people can start working with, all on the basis that, if you don't do something about the receding wetlands, you lose the agriculture and fisheries that these communities depend on. Then this is Davis Pond right next to, and you can see the scale here of what we're talking about next to New Orleans, again diverting water in that case, and then finally Bayou de Loutre out to the east. Now these are some diagrams that we did together with colleagues at LSU, trying to demonstrate what might be the regime for the plumbing diagram in a way, for what would happen under different scenarios. So this is if you have 1.2 million cubic feet per second of flow coming down here at the old river control structure. Currently, by law, 30% of it has to go down the Atchafalaya, 70% down the Mississippi, pushing that into various of these diversions following these percentage numbers, and then shifting it with the higher flow rates of 2.4 million cubic in big events, shifting more of the water into the Atchafalaya, diverting some of the water before it gets to the bird's foot out into Bayou La Loutre and down into Davis Pond, so that the amount of water ending up at the bird's foot is lower, but still enough so that you maintain the navigation. And then finally, in an extreme case of 3 million cubic feet per second, taking 50% of the water, so quite a bit of water, over to the Atchafalaya. So this was the model of that notion for the Mississippi. And you can see the cliff at the bird's foot, so this is why so much of the sediment gets dropped off. So representing those as well. And this is the book, which you can buy at Bill Stout. Thank you.
So like the archipelagos and the little slits and everything in the Hudson River Bay and all that for New York, I was wondering where the material comes from and does it add mass to the Hudson River Bay, or does it just take mass from underground? Like, does the volume of the Hudson River Bay change, I guess is my question.
Good question. No, I mean, it's a minor disturbance in terms of volume of water, the islands that we're talking about. I mean, it's something, but it's not that significant. You'd still have to do the modeling to show that the flows are not affected in a bad way, but.
Maybe talk a little bit about your early experiences working with Fuller, Taniguchi, Weiss, and all these amazing characters, and how that helped you to develop, say, your intuition as an engineer, and also give you the confidence to sort of stray a little bit off of sort of that given path.
Well, I went to work there because Taniguchi was a friend of my mother's, and when I was at MIT studying literature, I was under some pressure to get a practical degree, and I was looking around and not sure what to do, but I was thinking about civil engineering, and my mother ran into Taniguchi on the street and mentioned this to him, and he said, oh, well, he should come and work in my office because we just bought this building with Bucky Fuller, and he's moving his office down from Cambridge, and Bucky would be a great inspiration and so on. So I said, sure. And so I went to work in what's now the museum in the summer of '76 and helped actually build models for the show that was the inaugural show of the Cooper Hewitt, which Hans Hollein organized, called Man Transforms, and there was a room dedicated to Bucky. And so we built a lot of models of tensegrities and so on. Bucky wasn't around that much. Taniguchi was. And so talking to Taniguchi, who was quite, quite diverse in his interests and activities, you definitely get the feeling that anything is possible. I mean, there's actually, he, for example, he was involved in doing a sculpture garden for the Houston Museum of Fine Arts at the time, and I remember that he was getting prepared to go make a presentation of his design of the garden, and decided that it wasn't enough to design the garden, he also wanted to design the building behind the garden, which was going to be an art school. And so he had us build a model of his idea of what the building should look like, and showed up in Houston to the board of the museum saying, here's the design of what you asked me for. By the way, you've got to give me the building as well. And I heard later from Dominique de Menil that they were amused, but not entirely amused, and shot him down in no uncertain terms. Interestingly, now there's a competition for a new addition to museum, and one of the things they're thinking about is replacing that building because it wasn't that successful. So there's still a chance to do the Taniguchi building. So that sense of possibilities was very clear. But I think also, looking back later, I spent a little bit of time in Bucky's archives. What was striking both with Bucky and Taniguchi was that openness to lots of different opportunities, but also the way in which for all his interest in technology, Fuller was very much had the sensibility of an artist, and if you look at his drawings and his photography, he was an amazing photographer. He really had an eye and a hand, and his drawings are quite idiosyncratic, but quite beautiful. Lars Mueller published a book a couple of years ago of a lot of them. And so they overlapped in that sense and influenced each other a lot. And I think that to me was definitely a lesson in terms of the possibility of that kind of collaboration and mutual support and encouragement. And also, if you look at their correspondence, there's a lot of letters where Taniguchi is writing to somebody saying, there's this really amazing guy that you should consider for this and that project, Buckminster Fuller, and Bucky writing to somebody, this is incredible sculptor that, so they were constantly promoting each other and trying to find opportunities for each other as well. So I think that friendship There's a beautiful book that Shoji Sadao just published. Shoji was an architect from Cornell who worked for many years with Bucky and then eventually worked both with Bucky and Noguchi. Has written a very, very wonderful book reminiscing about that relationship. And I think just the range and openness and optimism that both of them expressed was inspiring. Continues to be inspiring.
I was wondering, you showed the examples of the kind of intense investment of engineering that somehow visually ends up being kind of completely non-apparent at the end of the day, let's say at the World Trade Center.
Mm-hmm.
And then in the larger projects, you kind of made the joke about the Dr. Seuss figure of the day. And then at the same time, you showed Venice and talk about mental mapping and the idea of the way that people understand the city either as fish or kind of the mapping of the transit lines around it. I'm wondering at this point when you're dealing with these much larger projects that have a lot to do with pretty sophisticated simulation, at what point do you start almost finding a necessity of inventing information to come up with a more simplistic reading, let's say something like the Dr. Seuss figure, because it actually just allows people to kind of key in or latch into what you're actually really after.
Well, I think that's the I think that's actually the lesson of both that project and the Mississippi project is that you can shift perception and expectations through visual material and analogies. And so I think your question about the displacement of the water by the land, there are lots of really important scientific questions, engineering questions, which we have not addressed. And in a sense, what we're doing is throwing down a challenge to the engineering and design community. What about this as a set of problems to deal with? And I think that's what that's where designers have a huge role to play politically, because for example, during the last election, there was a group of us that tried to organize architects and designers to be supportive of Obama, and we had a number of meetings. Max Bond and a few others, Adam Urinsky, and one meeting we presented our work on climate change, and then the second meeting we had at Max Bond's office, we talked about infrastructure and design excellence in infrastructure, and trying to translate some of the ideas that the GSA had pioneered in the 90s over to infrastructure design. And one of the things that Max said to us after we'd done this, and after the election, we all got together and said, "Oh, isn't it great?" And he said, "Well, don't stop. Keep using this group to mobilize support." And so we tried very hard for a couple of months. In fact, a whole group of us went to Washington, met with people, and continued to push on these topics. And the difficulty was finding a common language between our visual way of thinking and the policymakers. Most of them were interested in the representation of their ideas in a kind of new urbanist vocabulary, and that's as far as it went. It was very difficult to bring together the intention and aspirations that we were talking about, and the sort of policy economic thinking that was going on, and in the end, it didn't catch. I mean, it finally, I think, we failed basically to communicate. I'm not sure why, but for some reason the administration hasn't been very receptive to progressive design ideas, at least in my experience. And so I think the big issue is, how do you put things on the table? What we tried to do with the Mississippi, what we tried to do with the New York project, that will bend the policy discussion and create an objective that then both policy and research and scientific research can get organized around. Now, I mean, it works. I mean, I'm currently working with a whole group of people at Princeton putting together a big proposal to the NSF on actually starting to do the science that it's around this. So little by little, it starts to have starts to penetrate. Amanda Burden, the director of city planning in New York, has said several times that as she put it, this project altered the DNA of New York. So I think you can, and you know, she started talking about the water as being the sixth borough of the city. And so there's a way in which the sort of conceptual framework gets shifted by these visual projects ahead really of the facts, you know, in a sense. You know, we're sort of, it definitely has the cart before the horse, because there's a lot of issues that we don't know exactly whether we're right or not with our hypothesis, but it's definitely gotten things moving.
The beginning of your presentation, you present a lot of object-based projects, as you could say. And then as you move on, you get into the Mississippi and New York project, which are larger infrastructure designs and almost large network-based things. And I was wondering if you're providing some sort of narrative for future design, or almost a political and larger scale call to action for designers. Are you forecasting things for the future when you're designing things like that?
Well, I have a business to keep going, and the objects are more remunerative than the big ideas. I think one of the things that's motivated me lately is, you know, I think it probably goes back to 9/11. I mean, I had an experience working on the site after 9/11, and then participating in various ways in the redevelopment stuff. And I think it did affect me in terms of what I thought designers could and should be doing in situations like that. I wasn't very happy with the way in which architecture intervened and the relationship that existed between the political system and designers. So I think part of that motivated these different projects. But I think it goes back to what you were saying, that you know, there are a number of these situations where if you put something like this on the table, you can shift the discussion. I mean, another example that really influenced me a lot was in the 90s when the British government, British Rail, were trying to decide how to connect London to the Channel Tunnel with high-speed rail. They came up with a strategy which basically followed the existing rail lines. And a group of engineers from Arup, some of them retired, not quite sure why, but they started talking and took the initiative of proposing a completely different alignment that went to the east of London, across the river, and then came in from the north of London. And they mobilized and advocated for this alternate alignment, and eventually were successful in convincing the Parliament to change the plan. And then eventually, you know, and it worked for them, because eventually they got the commission to do this. But the citizenship behind that and the conviction that they brought to what was a better design was really inspiring. And I think, you know, among other things, it created the site for the Olympics, because they built a new tunnel and a new station, and the landfill of that filled this place where they're now building the Olympics, and did a lot of other things for London. And it was a good design idea. It solved a lot of problems simultaneously. So I think, you know, there's a lot of these sorts of problems that aren't addressed very effectively by lawyers and economists and other policymakers, where, you know, designers just have to step up. And, you know, if you see the mess created by so many other fields, you know, that there's a lot to do.
Any other questions? Thank you very much.
Well, thank you.